Hi and welcome to Unit 1 Topic 2 Video 4, and this is the first video about the scalar product. So the scalar product is a type of arithmetic. In previous videos we've talked about adding and subtracting vectors, which is pretty easy, particularly in component form. So now we're going to talk about multiplying vectors. Now vector multiplication is not quite as simple as we're used to in our standard counting numbers, or in fact any numbers, the real number system. Vector multiplication is just like it is for the real number system. It's defined by what we need it to do. So there are some beneficial ways that we can multiply vectors, but we've had to define it because it's not as obvious. So what's actually happened is we have a scalar product, which is quite handy, sometimes also known as the dot product, but we also have something called the cross product or the vector product, which we'll study in Unit 3. And they're both forms of multiplication and they both serve different purposes. As you can probably guess, the scalar product gives you a scalar result. So when you multiply two vectors using the scalar product, you get a scalar answer. When you do the vector product, you get a vector solution. But we'll get to the vector product. So firstly, the scalar product has an A, not an E. So it's one of a couple of options, like I said. So let's say these are the two forms. Let A be a vector and let it be A1, A2, and B be a vector, B1, B2. So A dot A, you'll remember or recall that I've stated that A scalar product B can be said or called A dot B, the dot product. So A dot B is equal to the A1 times B1 plus A2 times B2. So the top two numbers times by each other and the bottom two numbers times by each other added together. There's our simple definition of the vector product, the scalar product. But there is a geometric representation as well. So this is called the algebraic, and it's pretty easy. There's a geometric one, which is that A dot B is equal to the modulus of A times the modulus of B times cos theta. Cos theta is the angle between vector A and B, and it doesn't matter because cos has a even function properties, but it is the smallest possible angle. So obviously we have a second angle here, there, which I could use, but we use the smallest possible angle. So my next question is, can you prove that this is the case? And we can, and I'll do it very quickly for you now, but if you'd like, you are more than welcome, of course, to skip a little bit ahead and skip this proof. But for now, I'm going to connect these two up. So the proof relies on the idea that we have the modulus of A minus B here. Now, of course, I could do this as the modulus of B minus A, but the length is the same, doesn't matter which way the arrow goes here. So I'm going to say A minus B. Now, cosine theorem, or the cosine rule here, will tell us the following thing. The modulus of A, its vector, minus B, is equal to the modulus of A plus the modulus of B minus 2 times the modulus of A, modulus of B, cos theta, the angle between. And of course, all these things are squared. Well, not the second two there, but these ones. This is our cosine rule that we used in a previous video as well. It comes from the old c squared equals a squared plus b squared minus 2ab cos c. So we can use this to do a little bit of work in our favour. So what I'm going to do is do some recognition of what these moduluses actually show and build an understanding of what's going on here. So recall that the modulus of A is equal to the square root of A1 squared plus A2 squared. And the modulus of B is equal to the square root of B1 squared plus B2 squared. And the modulus of A minus B is equal to the square root of A minus B, A1 minus B1 squared plus A2 minus B2 squared. Okay, so things get a little bit out of hand now, but just remember that what happens when we square them, the modulus of A squared just gets rid of the square root sign. So that means that the first one is squared, so it's actually just A1 minus B1 squared plus A2 minus B2 squared. That's equal to the modulus of a squared, which is just a1 squared plus b1 squared, plus the modulus of b squared, which is b1 squared plus b2 squared, minus 2 times a1 plus a1 squared plus a2 squared times the square root of b1 squared plus b2 squared times cos theta. Okay, so we're getting there, and it's looking a little bit like what we want, but it's going to involve a little bit more expansion on our left-hand side. So here we get a1 squared minus 2a, smudged a little bit, I'm going to zoom in a little bit more here, a1 squared minus 2a1b1 plus b1 squared plus a2 squared minus 2a2b2 plus b2 squared equals all this stuff here. So in fact, I'll cheat a little bit and we'll drag all this across. Okay, now I can do some cancelling out. a1 squared, b1 squared, b1 squared, a2 squared. Oh, that should say a. No, it shouldn't. So that should say a. So this is a2 squared. This is a2 squared. This is still b. This is still b1 there. My apologies. So those two cancel. Those two cancel. That cancels the b1 squared. That cancels the b2 squared. And I'm left with these things. So I've got negative 2a1b1 plus minus 2a2b2 is equal to negative 2. Now, it's at this point that I recognise my folly. I didn't actually need to convert these out because my formula that I want involves moduluses. So negative 2 modulus of a, modulus of b, cos theta, just converted them back. And over here, I divide by negative 2 and I get a1 b1 plus a2 b2 is equal to the modulus of a, the modulus of b, cos theta, which is what we want. So this is the algebraic representation of the dot product, whereas this is the geometric representation of the dot product. So there's the proof, and you can skip ahead. You don't need to know that proof, but I think it's always important that you've seen these types of proofs and you understand that what we're telling you is true. Okay, so just moving on, there's a couple of notes here. And the first is that a dot b dot means multiply, scalar or dot product. You've seen this. The operation is designed to meet the needs of some context, including finding angles between vectors, super important. Work is F dot D, where F is the force and D is the displacement travelled. Power is F dot V, where V is the velocity and F is still the force. So power and work are closely related. And magnetic flux can be calculated by the magnetic field vector dot the vector area. So there's a few options there, and there are plenty of more, but they're some that you might run into in your senior maths or maybe senior science careers. So here's another important result, and that is that a dot b is equal to a1 b1 a2 b2. This was our algebraic result. And then a dot b is equal to the modulus of a times the modulus of b cos theta. That was our geometric result. But if we put those two together, equate those two right-hand sides, because if they're both equal to a dot b, then they must be equal themselves, we can rearrange and get this form inside the pink box, which is a great form for finding the angle between two vectors, an important feature of this. One last note is that polar form also holds in a nice way. A and B are R1 theta 1 R2 theta 2 as shown. Well, then A dot B is R1 R2 cos theta 1 minus theta 2. Now let's just go back up, or in fact let's just sketch that as a diagram and consider it briefly. And that is that we have A and we have B and we have theta. But if we look at A actually has a length R1 as denoted earlier and an angle of theta 1, whereas B has a length R2 and an angle of theta 2, and so the modulus of A is equal to R1. This is the modulus of A. The modulus of B is equal to R2. This is the modulus of B, and then cos theta is the difference between theta 1 and theta 2. So this works, and it falls perfectly in line, that does, with that formula. So there we have an introduction to the dot product. And what I'm going to do now is move on to video 5, which will explain how we can use it to solve some problems. All the best.